Yeah, right. So first, I want to thank the organizers for this great event, and I apologize for not being there in person. So I will talk about an exotic metal insulator transition. We call it MIT, and also a quantum bad metal. Let me first introduce my collaborators. So Nayan and Yichen, they are students in our department. And Xiao Chuan used to be the student when he was doing this job, but actually he is now a postdoc in Chicago. And Meng Xing used to be a postdoc in KITP Santa Barbara, and now she's moving on to a faculty member at the University of Utah. And then Zhu Xi is moving on to Harvard as a postdoc. And Chao Ming is now a faculty at Cornell University. So first I will introduce the motivation for this work. So mostly I will introduce why we are interested in two-dimensional transport or two-dimensional resistivity in general. That's because two-dimensional conductivity and two-dimensional resistivity, they are in general universal quantity. They are actually, they can be very universal. It means that they can be independent of the microscopic details. This is why this is the interesting quantity to look at. Then I will introduce some experiments in Moray system. So Moray system has been a very, very exciting and active subfield in condensed matter these days. So there are some very exciting experiments going on in some of the Moray system, which actually motivate our study. They observed a exotic metal insulator transition. So I will propose a theory for this exotic interaction-driven metal insulator transition, and I will explain why this interaction-driven MIT is interesting, and experimentally why these are a puzzle to answer. And eventually, I will also talk about our construction for a quantum bad metal. Yeah, of course, I will also explain what quantum bad metal means. First of all, in two dimensions, the electrical conductivity and resistivity in a purely two-dimensional system is a dimensionless quantity. Hence, it could be a universal value, which means that it can be universal, it can be independent of the UV details. So the first example is the quantum Hall effect. We know that the Hall conductivity is really just quantized as a quantized number times a universal unit, which is E squared over H. So actually, in many two-dimensional systems, the conductivity is actually a universal number times E squared over H, and the resistivity is going to be a universal number times H over E squared. This happens very often, actually. And actually, at the 2 + 1 dimensional quantum critical points or 2 + 1 dimensional conformal field theory, this electrical conductivity actually is the quantity associated with the low energy conformal field theory. Is something that people actually love to compute because it's a universal quantity. So it was first proposed that the conductivity, the critical conductivity at 2 + 1 dimensional quantum critical points is a universal quantity proposed by my colleague Matthew Fisher in the early 90s. And actually, it's actually observed in various experiments. So for example, this one actually, this is an experiment done in the early 90s. They were actually observing a phase transition between a superconductor and an insulator in a thin film sample, in a thin film superconducting sample by changing the thickness of the thin film, or by changing the disorder of the thin film. And actually, you can see that actually, so this part, the lower part, actually is it's an insulator. The upper part is going to be a superconductor. Here it's actually very big conductance. Here is a very small conductance. And at the critical point, you can see that the conductance is actually very well quantized, or very well actually at the order of 4 E squared over H. The reason is 4 E squared over H instead of E squared over H is because actually in this system, the charge carrier is a Cooper pair, which carries a charge number 2E instead of E. Okay, so it means that, this actually is a very good example, experimental example to illustrate that at 2 + 1 dimensional quantum critical point, the system can behave like a universal system, and the conductivity can be a universal number. Yeah, it's a universal number quantized. Sorry, it's a universal number times a e squared over h. And there's some other examples of a two-dimensional critical, two-dimensional conductivity being universal.
Sorry, there's a question.
Yeah, right. Go ahead.
Yeah, your plot here. Yeah. So here the frequency is much smaller than temperature, no?
Yeah, this is DC. This is DC.
Okay, so this isn't really the thing probing, the quantity Cj of the CFT in this limit.
Yeah, I know. Yeah, this is
okay.
DC. So yeah, okay. So this is the AC limit. This is the AC limit. Yeah, okay. Experimentally, well, I mean, this is DC. So this system has a lot of disorder in it. But actually, in this paper, they actually they propose that I mean, this quantity is actually so even a DC limit with disorder, it can also be a universal quantity. Yeah, but you are absolutely right that this quantity should be the opposite limit with omega over t goes to infinity. Yeah, okay, so there's another notion of bad metal, which was first pointed out by these two fellows. So it says that in a 2+1 two-dimensional metal, we have some very classical theory, semi-classical theory of metal to describe the metallic states of two-dimensional metal. So this theory relies on the semi-classical picture, which means that we assume there's a relatively good quasi-particle. So this actually, this picture relies on the fact that the mean free path, between two consecutive scattering from impurity must be greater than 1 over kf. So kf being the Fermi wave vector, and L is the mean free path between the two consecutive scatterings from the impurity. So suppose this standard or threshold is met, which means that L is greater than 1 over kf. This means that this conductivity evaluated using this very simple form must be greater than some number, or actually means that actually the resistivity must be smaller than a critical value. And this critical value is called the MIR limit, and this critical value is also as the order of h over e squared. So that means that suppose we observe a metallic state whose resistivity is actually far greater than this MIR limit. This is called a bad metal. And in the original paper proposed by these two gentlemen, actually the example was actually the cuprates superconductor at certain doping. So the resistivity of the system actually increases linearly with temperature, and at a certain temperature, the resistivity will cross the MIR limit, and the system will become a bad metal above certain temperature. Okay, so let me look at another example of a metal-insulator phase transition without interaction. So this is a example of metal-insulator phase transition caused only by impurity or disorder. So actually, in purely two-dimensional systems, suppose actually we describe an electron system without any interaction, then actually the metal-insulator phase transition is described by a non-sigma model in the replica space. And actually, eventually, we have to take the replica limit, which is n goes to 0. And in this pretty singular replica limit, actually, we may find that depending on the symmetry class of the system, there may be a metal-insulator phase transition controlled by the RG flow of the non-sigma model. And actually, the interpretation of this RG flow is that actually there's a critical point when the coupling constant of non-sigma model goes to 0, and another phase where coupling constant flows to infinity. And because in this non-sigma model, there's actually no small parameters to do expansion with, then these critical points will generally happen when the coupling constant is order 1. So physically, this means that the critical resistivity should be as the order of h over e squared. So this is the phase transition that we can understand, metal-insulator phase transition that we can understand without interaction caused by disorder. We know the critical resistivity must be as the order of h over e squared. And then suppose we go to another situation where the disorder is very weak, but interaction is very strong. Then actually we know that there can be a mod transition. which means that by tuning the ratio between the interaction and the kinetic energy, there could be a continuous phase transition between a metallic phase and a metal-insulator phase. The metal-insulator phase simply means that on every side of the lattice, there's a one electron, and because of the strong on-side Coulomb repulsion, the electrons do not want to stay on the same side at all. So it means that when we have precisely one electron per site, then actually the system becomes the insulator, because actually the electron cannot hop at all. So by turning on the interaction, there's a phase transition between the metal and a weak interaction, and actually an insulator, the metal insulator, and a very strong interaction. So so the theory for this metal insulator phase transition caused by interaction was proposed by these papers, and there was some very detailed and nice calculation in the last paper proposed. So the basic formula for this phase transition started with the parton construction. So basically, they decompose the electron operator into a bosonic parton which carries the charge, and a fermionic parton which carries spin 1/2. And then actually, so if you're unfamiliar with this parton construction, it's okay. You can just look at the bottom Lagrangian. So this is the Lagrangian describing this metal insulator phase transition. So basically, when R is greater than 0, when this tuning parameter R is greater than 0, it means that B will be gapped. Then actually, suppose B is gapped, actually the system will be just this F coupled with the dynamical U1 gauge field. And this F is correspond to a spin number. So basically, it means that the metal insulator is actually a spin liquid where there's a fermionic spin down coupled with a U1 gauge field. But actually, when R is smaller than 0, the B will condense, the dynamical gauge field A will be Higgs by B, and then the system will be described by just a fermionic particle F, and with a Fermi surface. So it means that actually the phase transition can be described by just the bosonic channel. So basically, the phase transition just the condensation transition of the parton B, okay, of the parton B. Okay, so we can also evaluate what happens to the electrical resistivity as the phase transition as the MIT in this theory. So this was very nicely calculated in the last paper here, and the calculation shows that actually the critical resistivity. I mean, suppose we assume the disorder is weak in the system, then actually we can show that the critical resistivity based on the locking rule is going to be a sum of the resistivity from the bosonic parton and the resistivity of the fermionic parton. And actually, if the disorder is very weak, the fermionic parton contribution to this resistivity will be very small as the critical point, but the bosonic contribution to the resistivity will be large. And then actually, eventually, the critical resistivity will be as the order of 7 or 8 times bigger than H over E squared. So this was the calculation done in the last paper. It's a very nice calculation. It means that the critical resistivity based on this theory will be as the order of 7 or 8 times H over E squared. That's the prediction from theory. Of course, actually, to perform the calculation, we need to take some large n and then take n back to 1. So there is some theoretical limit, which actually maybe they say some actual correction from the actual number. But actually, we can say that there's a small enhancement to the critical resistivity, which we expect, which is at H over E squared. Okay. Okay, so yeah, right. So yeah, this is the theoretical part. And so this is a previous theory for the interaction-driven MIT. So let me go to the experimental part. So starting from 2018, there was a very, very active subfield in condensed matter system, which is called a Moray system. So Moray system actually is a purely two-dimensional system. It's a so the first Moray system was basically a twisted bilayer graphene. So basically, people take like 2 layers of graphene and actually slightly rotate them a little bit away from each other. For example, in this in the first paper, they rotated by about 1 degree. So it means that the 2 layers of graphene will form a superlattice with a fairly large lattice constant, and the Dirac fermion of the graphene will actually be flattened a lot. So it means actually the bandwidth within the close to the Fermi energy will be very, very flat, will be very, very small. The bandwidth will be very, very small. And because the bandwidth is very small, the interaction effect is going to be very much enhanced. So this is a very good system. This is a very good system to actually test a lot of our understanding of strongly interacting 2D system. And actually in the last 2 years, many striking and very beautiful experiments and many beautiful phenomena have been found in these systems, including all these phenomena which I mentioned here, including strange metals, spin-treated superconductor, and many other phenomena have been found. Okay, so today let me talk about one experiment in one particular kind of a moray system in the transition metal dichalcogenide moray heterostructure. So actually, if you are not familiar with this material, it's okay. So we just need to know that this is the system formed by 2 layers of different materials, similar but different materials. And because these 2 different materials have slightly different lattice constant, they have a slightly different lattice constant mismatch, they will automatically form a superpotential due to this lattice constant mismatch. So that means that actually overall speaking, there will be like a super lattice, a super moray lattice with a lattice constant about 5 nanometer. And actually there was theoretical work which actually proposed that the low energy theory describing this system is nothing but an effective spin 1/2 Hubbard model on a triangular moray lattice. And actually there is a spin orbit coupling, of course, because the system actually has a relatively bigger has a much bigger spin orbit coupling compared with the graphene samples. Okay, so what they observe is that by tuning the ratio between the interaction and the kinetic energy, and the way they tune the ratio is by turning on some displacement field. Displacement field simply means that we turn on the electric field along the z direction, and they show that by doing that we can tune the ratio between the kinetic energy and the interaction energy. You can see that this is the plot of the charge gap. The delta is the charge gap. And we know that when a system has a finite charge gap, the system is insulated. And when the charge gap vanishes to 0, the system starts to become a metal. And the point where the charge gap vanishes to 0 is the metal insulator phase transition. So they show that by tuning the displacement field, indeed, the charge gap will vanish, continues to 0. And this T0 is the energy scale in the metallic set. But actually on this side, there's no charge gap at all. This T0 is just some other energy scale. So very beautifully, they can show that by turning on some parameter in the system, they drive a metal insulator phase transition of this effective Hubbard model on the triangular lattice. Okay, this looks good, but actually what happens is that this. So this is the plot of the resistivity versus temperature at various different displacement field. And actually this line, this brown curve corresponds to the critical point, And you can see that as the brown curve, you can see that at the 0 temperature, the critical resistivity is above 10 to 6 ohm. And H/E squared is about 2 times 10 to the power 4 ohm. So which means that so in this system, the critical resistivity is actually nearly 2 orders of magnitude bigger than H/E squared. Okay, so this actually is a striking phenomenon we found, because actually the critical resistivity is so much bigger than H/E squared, while the previous theory predict that the critical resistivity should only be like 7 or 8 times bigger than H/E squared. And also in the experimental paper, they have evidence to show that this system is indeed interaction driven, which means that disorder plays a perturbative role. So that means that actually this experimental finding suggests that we need to find a new theory for this interaction driven MIT, and we need to find a new theory to explain why the critical resistivity can be so big. And actually previously I have said that suppose a metallic system whose resistivity is far bigger than H/E squared, the system is going to be called a bad metal. So this means that in this system, close to the critical point, close to the MIT, the system is a very bad metal. So we need a new theory to explain why this 2-dimensional strongly interacting system has a large critical resistivity and why it's a bad metal close to the critical point. Okay, so just a comparison, we can compare the metal insulator phase transition in this system to an older metal insulator phase transition induced by interaction. in a two-dimensional quantum well. So this is the plot from a pretty old paper, and so this is the metal insulator phase transition in a two-dimensional electron gas, and actually it's a phase transition between a metal phase and also a weakened crystal, I think, by changing the carrier density. So you can see that at the critical point, indeed, the critical conductivity in this system is also as the order of E squared over H. Okay, also as the order of E squared over H. So it means that the current Moray system actually is pretty pretty exotic in this sense. Okay. Oh, by the way, since I cannot see the question from the audience, so let me know if you have any questions, so we can actually so I can answer anything which actually causes confusion. So well, okay, so our theory certainly has to be based on some assumption. And the first assumption that we make, which actually is a non-trivial assumption, is that the claim in the experimental paper is actually correct, which means that we assume that indeed what was observed is indeed a continuous MIT, and also it's an interaction-driven MIT, and also disorder plays a perturbative role in the experimental system. So our theory is based on these assumptions. Of course, suppose we relax or actually deny some of the claims, actually some other theories can be proposed. For example, suppose we assume that the disorder actually plays a very, very important role in the system. The system actually is very inhomogeneous. Actually, then actually one can propose another different theory, actually strongly relies on inhomogeneity. This was actually given by another different paper in a different group. So now let's say that we assume that indeed the system actually has a very weak disorder, and the MIT is driven by interaction. So the previous theory was actually based on a parton construction. So now let me just start with a slightly different parton construction as follows. So the previous theory is that we decompose the electron operator as a parton times a spin down. The parton is only one flavor parton times a two flavor spin down. But here, let me just make a very, very tiny modification to the parton construction. Let me just introduce two flavors of a bosonic parton, which means that C up equals to B1 times F up, and C down equals to B2 times F down. So it's a very small modification. And actually, the reason this parton construction is allowed in the system is because actually the system has no SU2 spin rotation symmetry. The system has a spin orbit coupling, and actually this parton construction actually breaks this spin SU2 symmetry, but preserves some other discrete spin rotation symmetry. Okay, but actually, this very small modifications to the parton construction actually leads to some important consequences. So, for example, the system actually is always at nu equals to 1, which means that we have one electric charge per Moray unit cell. And suppose we have one electric charge per Moray unit cell, it means that the total number of the bosonic parton per site must be equals to 1. This means that for each flavor of the bosonic parton, the filling will be 1/2. So for either B1 or B2, the filling of the bosonic parton will be half filled. Okay, then actually there's a very famous Lipschitz-Maddy theorem, which says that a half-filled boson cannot form a featureless insulator. It means that the mod insulator of the boson half filling must have some non-trivial feature in it. It means it must be either a topological order or spontaneous break certain translation symmetry. Okay, so the previous theory says that the phase transition of the MIT is just going to be a condensation phase transition of the bosonic parton B. Basically, the parton B will go through a phase transition between a superfluid and also a mod insulator. So here, because we introduced the two flavor of the bosonic parton, the implication, the consequence is that the bosonic parton must form a non-trivial mod insulator. The mod insulator of the bosonic parton must either break translation symmetry or have certain topological order. So let's see what's the implication of this Lipschitz-Maddy theorem in this case. So let me take a theoretically easier case, but actually may not actually be the case in the experiment. The theoretical easy case is that actually the mod insulator corresponds to a topological order of the bosonic parton. So we know that suppose the bosonic parton forms a topological order, then the quantum number of the bosonic parton can further fractionalize. So let's say that the bosonic parton will form a Zn topological order, and actually the n must be even. Okay, n must be even for some detailed reason. So suppose the boson form a topological order in the metal-insulator phase. It actually means that the electric charge carried by the boson will fractionalize to smaller charge carriers, which carry the charge E star equals to E over N. Rather than E, it's going to be E over N. Then it actually means that the critical resistivity as this new metal-insulator phase transition will be measured in the unit of H over E star square, which is going to be H over E square times the factor of N square instead of H over E square. So already you can see that there's a big factor enhancement due to the charge fractionalization. Okay, due to the charge fractionalization. So the phase transition now is going to be a phase transition between the Zn topological order of the bosonic parton and the superfluid of the bosonic parton. And actually, in terms of electron, the superfluid of the bosonic parton will be interpreted as the metal, and the topological order of the topological order of the bosonic parton will be the metal-insulator phase, and it's also a spin liquid of the electrons. Okay, so it means that actually the very simple modification of the parton construction will lead to the consequence that the charge will fractionalize, and then actually will give us a very big critical resistivity. Okay, so this is a simple. I mean, this is a theoretically convenient. Scenario, but actually, probably a more realistic scenario will be that the bosonic charge parton will form a density wave. It actually will break some translation symmetry in its metal-insulator phase. Yeah. So now this MIT, the metal-insulator phase transition, will correspond to a superfluid to some density wave phase transition. And actually, this superfluid to density wave phase transition is actually very much similar to the deconfined critical point between the Néel order and the valence bond solid order of the quantum magnet. So Néel order is the analog of the superfluid here, and the valence bond solid order is the analog of the density wave of the bosonic parton. So it turns out that actually this superfluid to density wave phase transition is the most naturally described using the boson-vortex duality. So this formalism was developed almost 20 years ago by Birkhoff and Balance. Yeah, so in the dual language, the density wave corresponds to a condensate of the vortex, and the superfluid of the bosonic parton is the insulator of vortex, because it costs a finite energy to insert a vortex in the superfluid. But actually, the density wave, the insulating density wave phase can correspond to vortex condensation. Okay, so actually the theory describing the vortex condensation, we can go to the dual picture of the vortex. We can view the vortex as a single particle, and actually the vortex condensation can actually be evaluated in the dual theory. So we need to calculate the band structure of the vortex, and actually here, because the bosonic parton is a half field, the vortex will see some fractional flux in its band structure, and the fractional flux seen by the vortex will lead to multiple minima in the Brillouin zone of the vortex. And actually, and the symmetry of the system will guarantee that the vortex will always have degenerate minima. We always have degenerate minima in its band structure. So, for example, here this is the dual theory describing this MIT. So every psi field corresponds to a vortex field, and because they are multiple minimum in the Brillouin zone, the psi will have a multiple component. We have an n component of the psi, n component of the vortex, and coupled to a dynamical gauge field A, capital A. And this capital A is actually the dual of the charge, okay, dual of the charge current. So based on this picture, you can see that if I integrate out psi, the effective action for A will gain a factor of n. So this means that if I calculate the dA correlation function, which is proportional to the conductivity will gain a factor of 1 over n. Will gain a factor of 1 over n because they are multiple components of vortex. because the conductivity gain a factor of n, factor of 1 over n, it means the resistivity will gain a factor of n. Okay, this is another scenario where the critical resistivity will be enhanced due to the non-trivial dynamics of the vortex. Okay, of the vortex. And actually, suppose we really calculate the band structure of the vortex, we can see that actually sometimes there's a degenerate ring in the Brillouin zone of the vortex. It means actually n can be very big and actually can be nearly infinite. Okay, in this theory, because actually there's a degenerate ring of the vortex in the dual band structure of the vortex. So actually the enhancement, although it's only a factor of n enhancement instead of a factor of n squared enhancement, the enhancement can still be very big. Okay. Actually, suppose we directly calculate the dA correlation. Actually, it's going. We are actually probing the conductivity in the limit. The resistivity in the limit where omega over t goes to infinity. Okay, omega over t goes to infinity. But suppose we want to calculate DC limit, then we have to perform some Boltzmann equation calculation to reevaluate the resistivity in the DC limit, and we also calculate it in our paper. And actually, this is the formula of the evaluation of the DC resistivity. You can see that there's also a factor of n enhancement here, factor of n times h over e squared. Okay. Yeah. So this is our basic picture of what happens as the metal-insulator phase transition. So basically, for some reason, we propose that actually the system, the electric charge will fractionalize as the critical point, and then at the critical point, because the electric charge fractionalize either due to scenario 1 or scenario 2, there will be an enhancement of the critical resistivity because the charge fractionalized. And then the charge fractionation should actually give us some pretty obvious experimental prediction. So for example, the prediction number 1 is that actually suppose we measure the transport gap. The transport gap is going to be controlled by the fractional charge, because actually the fractional charge is going to be the charge which carries it's going to be the charge carrier. But suppose I tunnel an electron in the system, but then the tunneling will be controlled by the gap of the electron. So that means that actually the transport gap and the electron and the transport and tunneling will probe in 2 different gaps. And these 2 different gaps should actually differ roughly by a factor of n, but actually it's not going to be precisely a factor of n because of the gauge field interaction and everything. But suppose experimentally we can see there is a clear difference between these 2 gaps. This can be viewed as a signature or sign of the charge fractionalization. Okay. And another different, more classic way of probing fractional charge, like how we probe the fraction charge of fractional quantum Hall effect, is the shock noise. Is the noise of the current is going to be proportional to the charge carried by the charge carrier of the current. So actually, by proposing the noise of the current versus the strength of the current, we can also measure the size of the charge carrier. There's also some other prediction about the quasi-particle weight close to the critical point, but this actually is probably difficult to measure experimentally. But actually, proposal 1 and 3 actually is more likely to be tested by future experiment. Okay, so this is the summary for part 1. So actually, we proposed a theory for the continuous MIT observed in the in some of the Murray heterostructure. And the theory predicts a critical resistivity which is far larger than the previous theory. And also we have some other predictions as well. And actually, there are some many other related works. So for example, there are some related works about the metal metallic phase and Wigner crystal phase transition at fractional electron filling. So far, I only talk about like the phase transition at the interior filling. Then we can easily extend our theory to the case where the electron filling is fractional, and actually this transition will be a metal to a Wigner crystal phase transition. And there are some other theory, as I mentioned, that suppose we rely on a very strong inhomogeneity. Actually, the system actually we can propose a different theory when the system has a strong inhomogeneity. Okay, the summary for part 1. So I will move on to the this part. But actually, I'd like to pause a little bit and see if there's any question about part 1.
Yeah, question.
Yeah.
Away from criticality on the metallic side, what sets the resistivity at 0 temperature?
What sets the resistivity at 0 temperature?
Yes.
That's actually mostly should come from the disorder. And also, of course, at a low temperature, at a low temperature, the gauge field will also come in. I mean, because actually at 2 dimension, actually the at 2 dimension, the metallic phase is the superfluid phase of the bosonic proton. But of course, we know that superfluid does not really exist in 2 dimension at finite temperature. So, you know, so it's at the finite temperature, calculation will be very, very complicated actually.
Do you have any comments on localization?
Localization? Actually,
Yes.
no, I'm sorry. Yeah, this is a strongly interacting system. So if we consider a strong disorder and a strong interaction, actually it's very complicated, I will have to say. So right. I mean, I don't have a clear picture of localization in the system. Sorry.
Thanks.
Yeah, so the theory we propose it based on the assumption that the claim in the experimental paper is correct, which means that the claim of the weak disorder is a correct assumption. Okay, so let me move on to the next part. So the experiment only revealed a metal insulator phase transition where the critical resistivity is actually very large. But actually, as theorists, we can go one step further. We can ask whether we can construct a stable metallic phase where the where the entire phase has a very large resistivity. It means that we want to try whether we can construct a bad metal phase, by playing with the vortex. So the previous theory, actually, the reason the critical resistivity is very big is because the vortex has some exotic dynamics. So here, let's try to see whether we can go even further and using the exotic dynamics of the vortex to construct a exotic bad metal phase. So as I said before, the original bad metal physics in Q-praise, actually the resistivity will increase linear with temperature and cross the bad metal threshold at finite temperature. Okay, so we are looking for a strongly interacting bad metal. And actually, there were a lot of studies which indicate that strongly interacting electron liquids is very difficult to study in the sense that they have no microscopic quasi-particles. So these systems may be described by hydrodynamics or holographic duals, pointed out by many papers, including this very nice review. Okay, so it's very difficult to study strongly interacting electron liquid and study their transport properties in general. However, we also know that for some strongly interacting systems, they may have some weakly interacting dual description. And in the weakly interacting dual description, there could be a trackable microscopic description in terms of quasi-particles in the dual picture. And the most famous example is something I have mentioned already, is the particle vortex duality, or we can call it a superfluid to photon duality in 2+1 dimension. And also this duality has been extended to many other examples in the last 5 or 10 years. Okay, so there was a very good observation made by Matthew Fisher in the early 90s. So it means that suppose the vortex is a good metal, the charge will be a very bad metal, because the charge conductivity is roughly 1 over the vortex conductivity. It's roughly 1 over the vortex conductivity. It means that suppose the vortex conductivity is very big, the charge conductivity will be very small. This is the observation number 1. And observation number 2 is that when the charges are strongly correlated, the vortex will be likely weakly correlated. The reason is that we can run the standard duality machinery. So we can say that the strong density interaction between the charge will become a 1 over G of the curl A square, and the G is the gauge coupling in the dual picture, and the G describes how strong the vortex should interact with the dual gauge field. And you can see that suppose V is very strong, the G will be very weak. It means that actually suppose the electron has a very strong density interaction, the dual vortex will have a very weak gauge coupling. Okay, has a very weak gauge coupling. Okay, so now this actually motivates us to actually construct a state which actually is the vortex is a very good metal. And suppose the vortex is a very good metal, it means that the charge will be in a very bad metal. Okay, charge will be very, very bad metal. And also, suppose the charge is strongly interacting, it means the vortex is going to be a very weakly interacting. Okay, so now we can imagine, we can ask ourselves, what is the best metal that we can have? Okay, the best metal will be a Fermi liquid, So it means that we will try to make the vortex a Fermi liquid. So this actually will require two jobs. Job number one is that we need to make a vortex of fermion. And the second, we need to make the vortex of Fermi surface. Okay, so both jobs need to be done here. We need to first make the vortex of fermion, and then we need to make the fermion form a Fermi surface. Okay, so here's how we do it. So it turns out that instead of making vortex of fermion, we can just make a fermion of vortex. Okay, we can just make so instead of making a vortex fermion, we can just make a fermion of vortex. So it turns out that in this kind of strongly interacting system, actually some formalism can naturally introduce the fermion, which again is a slave. So this was introduced in this standard SU2 slave rotor formalism for electrons. So this was introduced by Xiaogang Wen and Patrick Lee also in the 90s. So basically the spin up and spin down, they are to be decomposed into the F and the Z. And F is a two-component spin down, and Z they are two-component parton which carries charge. So again, F carries spin and Z carries charge. So actually, this formalism actually will actually have several different transformations. So for example, there's a spin transformation which only acts on the spin down. There's an electric charge transformation which only acts on the bosonic spin down, and there's also a gauge transformation which actually operate on both the spin down and also the boson. Okay, so now actually we want to explore some states constructed by the bosonic charge on the bosonic part on Z, and actually we can try to use the state of the Z to drive the fermionic spin on F into the vortex of the charge. So the way we do this is by making the bosonic part on Z1 and Z2 into a bosonic symmetry protect topologic state, or in other words, a bosonic quantum spin Hall insulator. So the bosonic quantum spin Hall insulator is described by this action here. So we have to introduce two U1 gauge field, and there's a mutual transition term here. And actually this term describes a bosonic symmetry protect topologic state and also a bosonic quantum spin Hall insulator. And because the bosonic quantum spin Hall insulator actually is gapped, it's safe to integrate out this two gauge field introduced for the bosonic SPT state. And after we integrate out the bosonic parton, what we are left with is this theory. Okay, is this theory. Again, the first term is the term we have seen before, is the spin down Fermi surface coupled with the U1 gauge field. And the second term is the consequence, is a topological response term from the bosonic quantum spin Hall insulator. It's actually, you can see that the A wedge DAE, and the capital AE is the external electromagnetic field. Okay, it's the external electromagnetic field. So this term is the key term in our construction here. And this term comes from the fact that we put the Z1 and Z2 into a bosonic SPT state. So what this term means is that the flux of the little a gauge field will carry the capital A charge. Okay, the flux of a little a will carry the charge, will carry the electric charge now, will carry a charge 4e. And because the flux of little a carries charge, then the charge of little a, which is the spin down, will automatically become the vortex. Okay, it automatically becomes the vortex. So now it means that by making the bosonic parton into SPT state, we have turned the fermionic parton into a fermionic vortex. And actually, the most natural state the fermionic parton can form is indeed a Fermi surface. Okay, it's indeed a Fermi surface. So actually, now we can say that okay, so we have turned the Fermi surface of spin down into the vortex Fermi surface. And also, suppose the charge density interaction is very strong, then the gauge coupling between the vortex is going to be very weak. So that means that although in terms of the charge, the system is very strongly interacting, But in terms of the vortex, the system actually is a weakly interacting system, and the vortex is going to be a good metal. So this actually can help us construct a bad metal of the charge. So indeed, we can just try to compute. We can try to compute the the electrical resistivity. So actually, here you can see that the electrical resistivity is pretty much the vortex conductivity, and the vortex conductivity can be very big, which means the electrical resistivity can be very big. And actually, by tuning some parameter, we can show that the charge, the electrical resistivity can be far bigger than the MRR limit. Okay, it can be far bigger than the MRR limit. And actually, we can use the very rudimentary dual theory to evaluate the resistivity. But now, actually, we are using the dual theory to evaluate the conductivity of the vortex, because the vortex is a weakly coupled theory. And by evaluating the vortex, we can actually infer the electrical resistivity from the formula. So this is the more detailed combination rule between the electrical conductivity and the bosonic conductivity and the fermionic conductivity. So actually, we can show that. So this is a plot of the electrical resistivity versus temperature, and the plot is in the unit of h/e². You can see that the resistivity can be far bigger than the MRR limit. And by tuning some parameter, actually, we can either have this behavior or this behavior, okay, or this behavior on the right side. So both actually are possible. So what are the other predictions we can make based on the state we construct? Actually, suppose we calculate the AC resistivity or AC conductivity of the system, we can show that the AC conductivity has no dual peak. Suppose we are at integer filling of the electron. But suppose we move away or dope away from the integer filling, we can show that actually the system will acquire a very small dual peak. And the dual peak will be proportional to the extra density of the electron square. The reason is that actually the extra charge density will now become the background magnetic flux density seen by the vortex. The vortex will now see an extra background magnetic field, and now the vortex actually moves so now we can use the basic dual theory to evaluate the conductivity of the vortex as if it's a charged particle moving in a background magnetic field, and using that we can actually infer the electrical conductivity, and we can show that there's a small dual peak emerging from the weak doping. Okay. Well, of course, there's many other effects one can predict. So, for example, we can see that in this system, based on the construction, what carries charge, does not carry the entropy. It's not the main entropy carrier, but the main entropy carrier does not carry charge. Okay, because actually what carries the entropy most is the vortex, but the vortex does not carry charge. So that means that the system, so what transport entropy does not transport the charge. So it means that there's no direct relation between the thermal conductivity and the electrical conductivity. And we know the relation between thermal and electrical conductivity is actually given by the Wiedemann-Franz law in the ordinary metal. But in this system, because the entropy is carried by vortex and the charge is carried by something else, the Wiedemann-Franz law will be strongly violated. So this was also proposed in other contexts. For example, the half of the Landau level, in the context of compositive fermion, because we know that as the half of the Landau level, the compositive fermion will actually be charge neutral, but it also carries the entropy. So in that context, the Wiedemann-Franz law will also be strongly violated. So actually there are many other previous works studied examples of the strongly interacting electron system as a vortex liquid. The most famous example is what I already observed. Sorry, is what I already mentioned. It was in the context of half of the Landau level. The compositive fermion can be viewed as a vortex, and it's a fermion. And also there are other proposals of understanding some previous experiment about the anomalous metallic phase in a two-dimensional thin film, which is the metallic phase between the superconductor and the insulator. And in this system, and it happens to have a very large conductivity of the anomalous metallic phase. And actually, there are also authors proposed a vortex liquid theory to understand this anomalous metallic phase between the superconductor and the insulator. Okay. So, so this is the summary of part 2 of the talk. So basically, we constructed a very bad metal by making the ferromanganic spin-on the vortex of the charge, and actually also by making the spin-on into a good metal. And because a good metal of the vortex is a bad metal of the charge, we can show that system actually has a very big and a finite resistivity at 0 temperature. And this is achieved by making the bosonic pattern a bosonic SPT state, and the bosonic SPT state will have topological response, and this topological response will make the ferromanganic spin-on becomes the charged vortex. Okay, and there are some experimental predictions of this bad metal phase that we construct this way. Okay, thank you for your attention.
Thank you very much. Is there any other question? Okay, I think people are tired. All right, let's thank Cenke again for the very nice talk.
Okay, thank you.